In this presentation, we will talk a hierarchical approach for joint extraction of entities and relations. First of all, I will introduce what the entity relation extraction task is. Entity and relation extraction are two fundamental tasks in NLP field. Detecting and extracting the structured triples from the unstructured document can support many other tasks such as knowledge base construction, information retrieval, and question answering. The concrete goal is to extract triple stack real E1, E2 from unstructured text, which means there's a relation real between entity E1, also called source entity, and entity E2, also called target entity. But some problems still remain in the previous methodology for entity and relation extraction. First, most previous approaches can't capture the interaction between entity recognition and relation extraction. Second, overlapping multi-relations in sentence are not handled well in many prior studies. Most of the existing methods assume that there's only one single relation in the sentence. Those approaches ignore the multi-relations scenarios, so their performance will be affected by the existence of multi-relations. Finally, prior studies about joint extraction of entity and relations are expensive to train. These models are task-specific and can't utilize the transfer learning method to initialize the parameter and save the computing resources. The entity relation extraction methods can be classified into two categories. The first class is the pipeline-based method. These methods regard name entity recognition and relation extraction as two independent tasks, which means relation extraction is performed based on the output of name entity recognition. There are several shortcomings of pipeline-based method, including error propagation, neglecting the correlation between two subtasks, and generating redundant information. The second class is joint learning method, which have received considerable attention in recent years. Joint learning methods use a single model to extract entities and relations simultaneously, which can utilize the close interaction between entity extraction and relation extraction. The novel tagging method shown on this page, which combines entity and relation information in the tags. This method completely transforms the joint learning model into a sequence labeling problem. It can extract multiple relations but can handle the overlapping relation extraction well, because each entity can only be assigned with a single label in this method. Copy-RE is an end-to-end model based on sequence-to-sequence method with copy mechanism, which can classify relation types from predefined relational tables or copy entities from original text at the specified time. But it can't extract complete multi-word entities and can't distinguish head entity and tail entity well. This method introduced a hierarchical reinforcement learning framework to solve the overlapping relation extraction problem, which decomposes the task into using high-level RL for relation detection and low-level RL for entity extraction. However, the training process for HRL is time-consuming and is hard to convert. In this paper, we propose an end-to-end joint learning method without any additional feature engineering. The proposed model with encoder-decoder architecture could capture the interaction between entity and relation extraction by introducing a hierarchical decoder, in which the low-level decoder is used to generate one or more relations contained in the sentence, and the high-level decoder is designed to detect entity pairs by fusing the information of relations generated from low-level decoder. In such way, extracting each triple can be separated in each low-level decoding step. Besides, our approach is configurable. We can apply different types of encoder, including popular BERT. Moreover, our model is equipped with hierarchical attention mechanism. One attention module in low-level decoder is used to improve the performance of a relation prediction, and the other in high-level decoder is designed to integrate the current extracted relation to obtain more accurate entity label sequence. Based on this unique design, our model can generate multiple triples in one sentence. Since each relation and entity pair is independently generated, our model will not be affected by the overlapping multi-relation situation. The contributions of our work are concluded as follows. First, we introduce a novel entity and relation extractor with hierarchical attention modules, in which the low-level decoder serves as a relation generator, and the high-level decoder combines the predicted relation information to complete the entity recognition process. Through this framework, our model can handle complex overlapping multi-relation extraction. Second, we design a configurable sequence-to-sequence approach for entity and relation extraction, in which we can utilize any contextual feature extractor, including some popular pre-trained models like BERT. Experiments on widely used datasets including NYT10 and NYT11 show that this method achieves the best results and further outperforms state-of-the-art with 7.0% and 7.6% improvement by introducing BERT respectively. As mentioned, our model is configurable. In the encoder phase, we can utilize different contextual feature extractors. Here in this paper, we use two types of encoder. One is based on bi-LSTMs, and the other is based on BERT, which is a pre-trained language representation model that has shown great improvements across various NLP tasks. From the encoder, we can obtain a fixed-dimensional semantic representation of the input sequence. The model uses the hierarchical decoder structure with a hierarchical attention mechanism to decode relations and corresponding entity pairs. For the low-level decoder, a unidirectional LSTM is used to generate one or more relations contained in the input sequence. Meanwhile, the low-level attention is aimed to score how well the input words and the current relation match. About the high-level decoder, this hierarchy is designed to generate a NER tag sequence according to the current relation. We adopt bi-LSTMs with CRF structure. CRF can learn the transition probability between tags, which has a certain constraint on the generation of adjacent tags. High-level attention is used to optimize NER tag prediction by making full use of the relation information. In detail, we use the relation embedding of current low-level decoding step to attend over the encoder representation. Thus, relation information is incorporated to help high-level NER tag decoding. From the picture on this page, we can see how our model works. Two widely used public datasets, NYT10 and NYT11, are used to evaluate the performance of different models. For both datasets, we filter sentences that don't contain valid triples. We adopt standard macro precision, recall, and F1 score to evaluate models. Our model is compared with several influential extraction methods, including normal tagging, copy-RE, HRL that mentioned before. The results of different methods on NYT10 and NYT11 dataset are shown in Table 2 and Table 3. It is noticeable that our LSTM-based model outperforms other methods in F1 score and achieves 1.6% and 4.6% improvement over the state-of-the-art HRL. After introducing BERT, our model has been further improved and exceeds HRL 7.0%, 7.6% on two datasets, respectively. In our experiment, we divide overlapping triple into two classes, entity pair overlap and single entity overlap. Entity pair overlap refers to a pair of entities having multiple relations. Single entity overlap means multiple triples share a single entity. As shown in the two tables, our model performs better in extracting overlapping multiple relations in both entity pair overlap class and the single entity overlap class. Again, after the introduction of BERT, the performance has been further improved. Compared with HRL, our model can extract more triples from data, which we believe is due to the nature of the RNN structure. We use LSTM as the decoder and set a special identifier end to indicate the end of decoding. When a sentence contains multiple relations, it is more likely to generate valid relations than generating end. To show the superiority of our method more explicitly, we show the prediction results of our method and select two representative examples to illustrate. The first sentence is in single entity overlap class. In particular, it contains two triples with the same relation contains, and our model can still extract the two triples correctly. The second sentence is in entity pair overlap class. Each triple can be generated independently by using the hierarchical decoder structure without being affected by overlapping entities. All of the above is the whole content of this report. Thanks for listening.